Taj is a research scientist at MIT DCI. He's a co-author of the Lightning Network paper. Taj leads DCI research focused on the scaling and interoperability of cryptocurrency and smart contracts. Today he will talk about discrete log contracts. Taj.
Okay, sounds good. Okay, hi everyone. Yeah, I'm Taj Gert-Jaap. I'm going to talk about discrete log contracts, which are private, scalable, smart contracts, sort of in the Bitcoin ecosystem or a UTXO set-based system. So quick intro. Yep, I'm Taj Gert-Jaap. I work at MIT. It's right near here. Lightning Network. This new work is discrete log contracts. A little bit about the DCI, since there's a lot of people who are maybe not from Boston. The DCI is run by the MIT Media Lab. We've got a bunch of core developers sitting over there who work on Bitcoin and are funded by the DCI. There's a lot of students. I just taught a class for undergrads too, so pretty cool organization. Come talk to us after if you're interested in working with us. Okay, so yeah, Lightning Network, I guess I don't really have to explain it because people have been explaining, talking about this in earlier talks today. It's a really cool way to sort of have these channels connecting different users that can make payments. And what discrete log contracts does is it uses a similar model, and in fact uses a lot of the same software, but has a totally different purpose. So instead of just being payments, these are like conditional payments. So it uses payment channels, and the idea of a payment channel is, okay, I can make a single output on the blockchain, and I can update it many times. And I don't tell the rest of the network about the individual, the state of this channel, but only the most recent state is what's broadcast when I close it. And I can revoke old states by revealing private keys. Conditional payments are a little different. The idea of a conditional payment is you could call it a bet, essentially. And working on this more, I sort of think of most financial things as bets at this point. So you could say like health insurance is you betting a company that you're going to get sick. And then the company bets that you're not going to get sick. And then if you win and get sick, they have to pay. And I sort of think of car insurance. Well, car insurance you have to get, but it really is me being like, but I'm going to crash my car. And they're like, but you won't. And then, hey, I crashed. Okay, you got to pay. So there's this external state that comes in, but basically it's moving money around based on some kind of data in the real world. So in this example, I'll just talk about weather. So let's say Alice and Bob want to bet on what the weather will be tomorrow. I think it's supposed to rain tomorrow, according to our weather reports that we have, but you never know. So Alice wants to bet that it's going to rain, and Bob says, no, I think it's going to be sunny, and they want to bet one coin. The problem, of course, is that there is no weather opcode in Bitcoin today. And I've been trying on IRC for years to get it soft forked in, but it's not going to happen. So what do you do? So Lightning Network is a simple script, and it enforces essentially that you have the most recent transaction. This is not counting the HTLCs and stuff. But I would argue that Lightning is made of smart contracts, right? They're fairly simple smart contracts. It's a couple different, couple opcodes, not too many things going on. But it is a smart contract. But one important part about that is there's no external data coming in. The smart contracts used in Lightning Network or in AMP or in all these different techniques, they're all built out of data that the participants in the network are creating themselves, right? So if Alice and Bob make a Lightning Network channel, they're making up keys. They're sending each other public keys and hashes and pre-images. All this data that they're sending comes from them. There's no external state, right? But if we want external state, such as like, what is the weather today? We need some way to get it, and usually that's called an oracle. So the simplest oracle you can think of is multisig. Or really, the simplest oracle is you just say, we're not even going to use an oracle. So 2 of 2 multisig would be just Alice and Bob both send their money into some kind of channel or a multisig output, and then based on the weather tomorrow, they agree to sign off on who gets the money. This works with friends, but Bitcoin is the currency of enemies, right? So if you actually have a contentious resolution to this where Alice says, okay, it rained, pay me. And Bob's like, no, that totally doesn't count as rain. There was like 2 drops. That wasn't even rain. This is a real problem. There are some designs I've seen, some papers about doing this kind of, Oracle-less contracts. But there's a lot of issues with it where like rich players are an advantage because they may have a lower time value of money. Where if they don't agree, the funds are frozen. And maybe Bob's really wealthy and has no particular need for this coin anytime soon. And Alice has to pay her rent by the end of the month. And so Alice is like, look, I maybe shouldn't be gambling while my rent is due. But anyway, it was raining and pay the coin. And Bob can say, well, how about I pay it to you next year? But if you want it this month, I'll give you 0.5 coins and I get 0.5 coins. And Bob can sign all sorts of time-locked transactions, which would then allow Alice to get a little bit less of the money if she wants it sooner and more of the money if she wants it later. And it's hard for Alice to respond to that kind of a sort of hostage situation. So there's a lot of issues. You need some kind of third-party arbitrator. So what you can do is the simplest case would be a 2 of 3 multi-signature oracle. So then you'd have an output with 3 keys. You'd have Alice, Bob, and Olivia. Olivia is the oracle. So if Alice and Bob, and so this is, like Sharon was saying, an optimistic protocol where if Alice and Bob are cool with each other and they both agree, okay, it rained, we'll move the money, they can both sign. They don't even have to contact Olivia. Olivia is there in case they're fighting. And if they fight, or even more likely than fighting, is one of them's just unresponsive. If Bob just turns off his computer and goes somewhere on the weekend, and Alice is like, hey, come on, sign, I won, and he's just not there. So in the case of uncooperative or offline, they can ask Olivia to sign. Either Alice or Bob can ask Olivia to sign. The problem, however, is if it's sunny and, I think that should be Bob. Anyway, Alice tells Olivia, hey, it's Alice, say it's raining and I'll give you 0.8 coins. Right? From the Oracle's perspective, well, is the Oracle getting paid? Maybe a little, but in the case where the Oracle's dealing with funds much larger than any kind of fee that they're charging, there's a lot of potential for bribery where either of the parties, especially the losing party, can say, hey, I'm going to lose this. I'm going to lose everything. Instead, I'll try to make a deal with the Oracle to ask them to sign that I won and give the Oracle a big cut. And then that's pretty ugly. So 2 of 3 oracles, it could work. For some use cases, this is okay. If the Oracle is like a well-known entity and these things are, people trust them. This is sort of how a lot of legal things work today, where you've got some kind of third-party arbitrator or some kind of escrow agent. Like, it's doable. It works. But we can do a lot better with the technology, in Bitcoin. So the problems in this, not only does the Oracle see every contract, they also decide the outcome of every contract individually. And they can equivocate. So that means they could say it's sunny over here and say it's rainy over there. And there's no way to sort of track these things and sort of point out that, hey, this Oracle was lying. They were saying 2 different things. So it would be better if the Oracle couldn't equivocate. And even better if they never saw the contracts at all that they were helping to decide. But how do we do that? So there's some fun mathematics involved. Basically, I'm not going to go into all the sort of math details, but you can use a signature where you pre-commit to the randomness that Sharon mentioned before. There's randomness involved in all of these signatures, which makes them malleable. One way to actually, to some extent, remove the malleability is to pre-commit to that randomness before you sign. So in the process, instead of just giving someone a public key, you give them the randomness you're going to use for your signature. That commits you to a single signature for that key pair. If you sign twice, you will then reveal your private key. But what it also does is it allows any other parties to sort of pre-compute what your signature will look like. They can't forge a signature on your behalf, but they can see what your signature will look like. They can basically get a public key version of your signature. They can get a public key to which your signature would be the private key. And this is really cool. So what we can do is use that in a setup similar to Lightning Network channels. Okay, so recap at this point. But in the Lightning Network, you've got these states, and you invalidate them by revealing private keys. Right? So the first state is Alice has got 1 coin, Bob's got 9. And this is a transaction spending the funding output. Then you build a new state where they each have 5, and then you invalidate and revoke the old state. Both parties reveal a key such that if either of them try to broadcast this state, they will lose all their money to their counterparty, right? So there's this timeout in the script where, Alice has to wait a day, but Bob can grab it immediately because now he's got the keys to do so after it's sort of invalidated. However, in the current state, they would each have to wait a day. They don't have the sort of revocation keys to immediately spend it. And then you can, you keep building new states and revoking old ones by revealing private keys. What discrete log contracts does instead, let's say there's 3 different states, sunny, cloudy, and rainy. And they've got these different payouts. The third-party oracle signs a message, and that message is just the word cloudy, for example, and then publishes that signature. Maybe it's on a radio station, maybe it's on a website, but in a way that's broad, right? They don't know exactly what contracts they're dealing with. They just say, okay, today's weather is cloudy. Or similarly to, they could post a price. Okay, the price of oil today is $53 a barrel. They sort of know people are probably going to use this information in their contracts, but they don't know the individual ones. That signature is the private key that allows the sort of revocation, output for these transactions. So whereas in Lightning, the revocation way is sort of the wrong way, where if someone tries to defraud you, you can say, hey, I've got the private key for that, and grab the money immediately. In this case, you use that part of the script to say, hey, I've got the oracle signature. I can now grab this money immediately, and so broadcast it. If you do not have the oracle signature, so for example, if Alice were to broadcast the rainy state, she just wouldn't be able to get the money at all, ever. And Bob would be able to take it all after a day or so. So the worst you can do as an attacker in this system is I can delay my counterparty, right? I can be annoying and make them wait a day when they shouldn't have to, but then they get all the money. Okay, so this is pretty useful. There are limitations where you have to sort of pre-commit to every possible outcome. So, So you're probably going to actually have a lot of different states. Most of the time, people are not going to be betting on the weather. I think they're going to be betting on numerical data, such as a price. And what we have is the price of dollars, essentially. So you're going to have a lot of states. It gets a little ugly, but computers are pretty fast. And all of this is off-chain, right? The only thing that ends up on the chain is a single final transaction. And what's very nice is that the transaction doesn't reveal anything about the contract, right? So if you just see, oh, Alice gets 5 coins, Bob gets 5 coins, who knows what was going on there? The oracle themselves cannot tell that their oracle signature was used to validate this transaction. So that's a nice privacy property of it. Another thing you can do is you can put discrete log contracts within channels. So similar to having a bunch of HTLCs in a channel, you can have further 2 of 2 multisig outputs within a channel, and then from there, those build lots of different state transactions for discrete log channels, discrete log contracts. And in those cases, if the parties cooperate, they can, similar to clearing out an HTLC, they can clear out a discrete log contract and just update the balances of the parent channel. So if that works, then nothing goes on chain at all. No one can tell that there were these contracts going on. If it doesn't work, then you have to close the channel. Then you've got these other outputs that look like sub-channels, and then close those. So it does, add to the data when people are not responsive or not cooperative. But in the optimistic case, it can be help for scalability a lot. Another thing you can do is the question of oracles. Who are these oracles? Do we really trust them? I think in practice, in real life, you're going to have trusted oracles. One of the most easy would be an exchange, where you can, if a lot of people are trusting the exchange to hold on to their private keys and hold on to their coins, you can probably also trust them to report what the price of Bitcoin was that day. That seems like an easier thing to trust. That seems like not as risky. But things can happen. Oracles can get hacked. Someone can report the wrong price to try to wreak havoc on all these different contracts. So what you can do is you can use multiple oracles. You can basically add their signatures And it's literally just addition modulo this big prime. So it's pretty quick. And for n of n, so if you say, I want these 2 of 2 oracles to have to agree in order to execute this contract, that's easy. There's no actual size increase for the contracts. If it's like 2 of 3, it gets a little uglier and gets bigger. But I think this can help a lot in that if one of your oracles gets hacked, then the contract could sort of revert and both people get their money back. So we have a demo, and then I'll describe the first use case. So we're going to talk about Bitcoin settled dollar forwards. And like the Chicago Mercantile Exchange and maybe CBOT have Bitcoin futures. And that, I believe, was early this year or late last year that they used their existing infrastructure to be able to trade Bitcoin futures. But what that really means is there's no Bitcoin involved. You're basically trading a derivative that's cash settled. And by cash, they mean dollars, not Bitcoin Cash or Bitcoin. So basically, you enter into a contract, and people are doing this today, and there's millions of dollars going on with this, where you say, I want delivery of 10 Bitcoins at the end of the month. And you won't get 10 Bitcoins, but you'll get the dollar value of 10 Bitcoins based on a bunch of different exchanges. So what we're implementing is dollar futures. You can get $100 US worth of Bitcoin at the end of the month or the end of the week. And what you do is you fund the contract with a counterparty, say, okay, I want dollars. And the flip side of that is someone wants super volatile Bitcoin. So the idea is, okay, if the price of Bitcoin goes down, I want even fewer of them. If the price of Bitcoin goes up, I get even more of them. That's the volatile side. The inverse side is, if the price of Bitcoin goes down, I don't care. I just get more of them, such that my dollar value of this output of this smart contract is constant. So I think this would be pretty useful. I think people are going to want to use it. Looking sort of in this ecosystem, there's things like Tether, which sort of act like, there's a lot of interest in stable coins. This is not exactly a stable coin, but it allows people to trade and reduce their volatility or increase their volatility. And without trusting their counterparties. They do have to trust an oracle, but they don't have to worry that their counterparty is going to run off with the money or that their counterparty won't cough up the dollars they're supposed to at the end. We've been working on it, a bunch of people at the DCI, and Gert-Jaap is one of the programmers of this demo we've got so far, and he's going to show us how it works. Thanks. You need to plug in there? Or?
Yeah, I was supposed to be able to plug it in. Oh.
Okay. I guess. Okay. FCAT.
Oh, it's not my second screen. All right, so what you see here is this is sort of our under development UI for LIT, which is the Lightning Network implementation that we're working on at the DCI. And what you see is 2 nodes. We have Alice on the left with a connection to Bob, and Bob on the right with a connection to Alice. And Bob and Alice want to engage in a dollar future or dollar forward. So what we do is we start a new contract, and Alice can say how much dollars she wants to buy from Bob at what time in the future. So in this case, it's going to be in the past even. Well, that's easy because then I can settle it right away. What we use here is an oracle that randomizes the value of Bitcoin to sort of emulate volatility. So I want to buy $10,000 at a price of 8,130. That's actually in Satoshi per dollar. So there's what the oracle will tell us is how much Satoshi we have to pay for $1. So the smallest denominator of Bitcoin. And so Alice is predicting she wants to pay, I think it's 12,300 Satoshi per dollar. So when I save this, we're going to propose this to Bob, who still has to accept, obviously. So Bob receives an offer from Alice to buy from you $10,000 at a particular time in the future And that requires 1.23 Bitcoin to fund the contract. So both participants have to fund the contract. And at the end, when we settle, then based on the actual value of the dollar, either party gets either more or less Bitcoins. But there is a limit in the bandwidth. So if Bitcoin in this short time skyrockets too far, then one side gets all the value in the contract, but it might not be sufficient to cover the value difference. There's a limited bandwidth. So when I accept the contract, it's building the contract, it's exchanging the signatures, like what Tej was showing, that for each possible value of the dollar denominated in Bitcoin, it exchanges the signature and the transaction that divides the value in the contract between the two participants. And what happens on the blockchain, this is my my rec test blockchain. So what you see at the bottom is the transaction where Alice and Bob both have 5 Bitcoins in their wallet. And they both sign a transaction that creates the contract output and their change outputs back to their wallets. So at a time in the future, we're going to settle the contract. And well, what this UI does, it fetches the value from the Oracle automatically together with its signature. The value of $1 is 12,700 Satoshi. And the result of that is that Alice gets 1.27 Bitcoin and Bob gets 1.19. So because I think this means that the Bitcoin price went up, so or it went down, so Alice gets more Bitcoin to compensate the difference. And both of these sides can settle the contract at their convenience. So when either of the two sides decides to settle, they have all the signatures to settle. So now the contract is closed at the left side, and once a block is mined, the other side can also claim their Bitcoin back to their wallet. And if we then look at the block explorer, we can see that this was the contract output. So the contract was 2.46 Bitcoin. This was the division that we agreed upon at the start of the contract, that if the value of the dollar was X amount of Satoshi, then this is how we divide it. But because of the potential that somebody publishes the wrong transaction, there's a time lock on this output that if it's wrongly published, we can claim it after a day or after the timeout. So both participants also claim their output back to their wallet, back to the keys that are under their full control. And that's basically it. So now we started out with 5 to 5 Bitcoin, and now they have a different division after the contract was settled. And that's it. And we even have 2 minutes left for questions.
Yeah, we have okay. I have one. Maybe you can use a microphone there, or if you can, or you can be loud.
They both ended up with more money. That's because Bitcoin went up?
That might be the case. Well, actually these, you mean the dollar values?
Yeah.
Yeah, so the dollar value is actually from a live feed from, I think, Crypto Compare or something. But the value while creating the contract is randomized, and also while settling it is randomized. But if I was to randomize this value that you see, then the demo would be a bit weird because you see the value go up and down all the time. So if they both have more dollars, that means that Bitcoin was going up.
Does the contract specify the bounds, like the protocol specifies the bounds of the output, or is that
basically
determined by the users?
It's basically like the easiest way to do it initially is symmetrically fund it. So Alice puts in the exact same amount as Bob, and so you're okay up to a 50% increase in the price of your asset. Well, another way to put that is a 50% decrease in the price of Bitcoin. You know, there's in the software you could definitely change that, but right now for just the easiest way, they both put the same amount. Other questions?
Does the Oracle need to pre-commit to a large number of prices for this to work?
So no, the Oracle needs to pre-commit for anything they're going to sign, they need to pre-commit one key, essentially one elliptic curve point, the randomness for their signature. So if the Oracle is signing lots of different things, like, so for every stock, for example, if I'm going to say, I'm an Oracle, I'm going to sign the prices of all the stocks in the S&P 500, then you'd need 500 different points. And they're 33 bytes each. So it's pretty compact.
So there's a range of prices that the US dollar prices that Bitcoin would have wound up at, right? And then the Oracle has to sign for whatever price it observes.
Yes.
So does it need a pre-commitment for everything in that
No,
range?
it pre-commits to one. It says, here's the key I'm going to use to sign what the price of the dollar is tomorrow at 5 p.m. And then the actual message being signed is just, okay, it's $8,100. So one point per each signature that potentially, but not for each possible message being signed.
Okay, last question. Do you have this working with ECDSA, or are you using a modified Bitcoin?
So it uses Schnorr, the Oracle uses Schnorr signatures, but the Oracle is sort of offline, and then you can, and ECDSA still has the property where you can add public keys and like add private keys. So it works today with ECDSA, but the Oracle themselves are using a modified Schnorr signature. Cool. Okay.
Yeah. Perfect. Thank you.